All right, so we got something kind of interesting here. We've talked about vector functions, and what we know so far is that these vector functions, what they create are in general these curves through space. So go pretty much anywhere through space, and we've learned how to find derivatives, which of course you know as the tangent to a curve at any point, basically at any time, because our parameter is t. So what we've done so far in this chapter is found vector functions, we've sketched a couple of vector functions, we found derivatives, and we realized that what that derivative is giving us is, instead of the slope of the tangent to a curve at a point, it's the direction of the tangent to a curve at a point. Head nod if you're with me on that one. Now we're going to talk about something just slightly different. What we're going to talk about here is, what about the length? Can we find the length of one of these space curves? Well, in calculus, what is it, Calc 1, the very end of that, we started talking about parametric equations and lengths of curves on a plane. Well, we're going to extend that concept today. We're going to find the lengths of a curve that's not on a plane. Is it hard? No, but then we do something really interesting with it. We start talking about, can I take that arc length and reparameterize a vector function? Now, if you're like, what? You're making up words now, man. I'm not making up words. A parameter of a vector function is t, yeah? What if we change the parameter? What's that do? How do we do that? What does it mean when we do that? We're going to talk about that for the last part of this section. Then we talk about movable frames. We're not going to get there today, but later on we will get there. So let's bring some stuff back from Calc 1. Very end of Calc 1, when we talk about, maybe it's Calc 2, isn't it? Parametric. We talk about Calc 2. We talk about length. When we talked about arc length for parametric equations from Calc 2, so arc length from parametric equations, it looked like this. First glance, kind of looks like a nasty little formula, but when we really think about it, listen, if you're on a plane, we got a square root of square plus square. That has a lot to do with the distance between 2 points. Well, if you integrate, it makes the distance between those 2 points ultra small, and we add up those distances along the curve. It's giving us the length of the curve. That's if it's on a plane. Well, what's really nice, and by the way, this is for not x and y being between here, but the parameter t. This means t is an element of a to b. That means just basically t is going from a to b. That's what that says. And that's from Calc 2. So here's the nice thing, though. In Calc 3, the extension it's really intuitive. It's really just one little piece. So now we're going to go, what about on not just parametric equations, but vector functions, stuff going through 3D? Can we also find the arc length? The answer is yeah, and it looks really similar. We still got an integral. We're still going from a to b. It's still talking about the parameter t. It's still a square root. It's just here's the thing. Here's the thing. If you're on a plane, how many variables do you actually have on a plane? That's 2D. How many do you have? In 3D, we have 3. So if we just add that third dimension, so hey, if you know, it hopefully works for you. F is the what component of a vector function, and G is how can I represent Z? If we just add that component on there, basically, if you check it out, if you look at it, take the component, take the derivative, square it. Take the next component, the y component, take the derivative, square it. Take the next component, the last component, the z component, derivative, square it, take the square root. Listen, if you just think distance formula, you basically have it. Do you remember, you better find it, I hope you remember finding magnitudes. Goodness, does it look like a magnitude?
Yes.
It's just the magnitudes of those derivatives. So derivative, square them, add them, square root them. It's basically the distance formula. What's happening here is you're taking little teeny chunks. That, I mean, they're super small, okay? Little teeny distances between points. You're finding the distance there, ultra small, and adding it up along the space curve. That's what's happening here. We're not going to go in the derivation of it, but it's this idea. If you want that idea, you look back at the Calc 2 videos, extend it into 3D. Show of hands feel okay with that one. Now, I'm going to tell you something. This is weird for me to say this, but don't ever use this. Ever. Ever. What? Why do we even talk about it? Firstly, well, you need to know where it comes from. Okay, you know what this means. This is the Calc 2 idea, distance between points, and then we integrate that across a curve. It's giving us the length of the curve. Distance between points practically, then we integrate it along the curve. It's just giving us the length of that curve, or arc length. That's what that means. But wait, check this out. A vector function itself is defined like that. We literally just talked about it. So yeah, the f is the x component, g is the y component, h is the z component. We'll check this out. If we take a derivative, watch carefully though, I don't want you to miss it, all right? If we take a derivative, what we learned from the last section is derivatives of vector functions are super nice. You literally take derivative component by component. It's pretty easy to do. There's no fancy formulas or rules or anything. You take the derivative of f, take the derivative of g, likewise for h. Pop quiz, what's it mean right now? What's that mean? What is the derivative of a vector function? What's it mean? That's a tangent. So this is the tangent vector to this curve through space at any point. But check this out. What if we wanted to, and we did this, you remember from unit tangent normals, the only reason why we did unit tangent normals last time was for this idea right here, was to be able to do this. Do you remember how to find the magnitude of that? Do you remember doing it that one time that we did it? Last section, right? We did this one time to find the unit tangent normal. How would you find them? Well, let's see. Is it still a vector? Come on, people now. Is this still a vector?
Yes.
You see the isolation cage, right? Can you find the magnitude of a vector?
Yes.
Tell me, how do you find, in your own words, how do you find the magnitude of a vector?
Square components and add them square root.
Square it, add it, square root it. Okay. And we mean components there. Square it. Square it. Add it. Square root it. True or false? That's the magnitude of whatever that vector is, that tangent vector. This is the magnitude of the tangent vector. Head nod if you're with me on that one. What? Why don't we ever use that? Because this formula gets a lot easier if you can talk about vector functions, which we are talking about vector functions. Then we go, hey, you want to find the arc length? You want to find the length of a space curve? Here's what you do. Find the derivative of the vector function, find the magnitude, go from A to B for however long you want to find the length of the curve. So for t equals A to B. That's why I say don't ever use this. It's the same thing, but this wraps everything up for you, and it gives you a better way to remember it. So arc length says find the tangent vector, find the magnitude. Then you integrate. So if you feel okay with that one. So this is what arc length really is how we find it. We took a 2D idea, we extended it to 3D, but we have a better way to represent it. Find the magnitude of the derivative of the vector function and integrate. So what we're going to do right now, two pretty quick examples. Then we'll talk about this next part, how you do arc length parameterization, like what in the world that means, and why we might do it. So we're going to make it there, and then we'll probably stop for today. If we have time, I'm going to do a pretty heavy-duty example. If not, let's do it next time. So here you go. First example. Let's do this one. So I'm going to find the arc length. Find the arc length for that thing on this interval. I'm going to make a little pause right now. I'm going to come back over here for a second because I want you to understand something. This formula right here is going to give us one of two things. The actual arc length, please listen carefully, the actual arc length, if I'm going from value of t to value of t, it's going to give us the actual arc length. Or if I don't go from value of t to value of t, so basically the difference between a definite integral and an indefinite integral, it will give us the arc length function, something that still has t's in it. Does that make sense to you? That arc length function is what we're going to use for arc length parameterization. That's the function. So what this gives us one of two things. Number one, if we're going from t, or taking t from a to b, it's going to give us actual arc length. So it gives two things. Number one, can give arc length. That's for t going from a to b. Number two, if you don't do the definite integral, if you don't go from like 0 to 2 pi, if you just leave it in terms of t, that's going to give us what's called the arc length function. So the actual arc length, that's when you're finding L, the arc, just the length of the space curve from a time to a time. Or it can give arc length function. It would still have t's. So it still has the t in there. When we find the arc length function, we don't call it L anymore. That's like the L, I mean, that's got to be numbered. That's got to be like the length. When we have the arc length function, we call it S of t. And whenever we see that S of t, that's going to stand for the arc length function for us. So just a little bit of a recap. We know that this is basically distance formula. It's practically what it is. From parametric in calculus 2, now we have 3D calculus 3, it's still parametric. But we also know that this thing is really just the derivative when we take the magnitude. If we integrate that, we get two options. If you're going from number to number, you're actually finding a length. That's case one. You actually find the length of the space curve from this point or time to this time. Head nod if you're with me on that one. If you don't go from A to B, if you just leave it in terms of t, because this is going to have a t in it, you're integrating, right? You're going to get some t's out of this thing. If you leave that in terms of t, that's called the arc length function. And we're going to use that to do arc length reparameterization in just a bit. Does that make sense to you? So right now, what are we finding? If I'm actually going from 0 to 2 pi, am I finding the L or am I finding the S of t? What am I finding?
L.
The L, because I want the actual arc length. Do you guys see the difference there? Okay, cool. So let's go ahead and set it up. What's the first thing you might want to do?
Take derivative.
Go ahead and do that. Take the derivative. A lot of times we get wrapped up, we forget what we're doing. When you take a derivative, what are you exactly finding? What is the derivative?
Tangent.
Good. So we just found the tangent vector to this curve at any time that I want. That's what we found. So the instantaneous heading, instantaneous direction with the magnitude, how fast it's going to a certain point, and the direction. That's what we're finding. So hence feel okay with that. Is that relevant here? Well, no, not really. It's just part of our formula, but that's what we're doing. What's the next thing that you would do to get our arc length?
Magnitude.
Can you find the magnitude right now? Go for it. Start it. At least set it up. So let's see. We square them. We add them. We square root them. Derivative squared. Okay, so component. Derivative of component squared. Derivative of component squared. Derivative of component squared. Square root of them. I want to know if you made it at least that far. Show hands if you did. You can see what's going to happen, right? With a lot of the sines and cosines, when you square sine and cosine, you're going to get a whole bunch of identities on a lot of the stuff. So when you have vector functions, you got sine, cosine, and you start taking derivatives, you still get sine and cosine. And then you start squaring them, you get sine squared, cosine squared. Do you guys see the identities that work right here? Especially when you add them together, you're going to get a lot of sine squared, cosine squared. Look for that stuff. Especially if we get the same number, man. That's pretty fantastic. Let's go ahead. Let's factor out the 16. Everyone in the class right now, you got to know it. You've known it since trigonometry. How much is cosine squared t plus sine squared t? 1. So this ends up being 16 times 1 plus 9. How much is that whole thing? What is that? 5. Yeah, it's square root of 25. We got 5. I want to know if you guys are okay on the math so far with this. Not too bad, but you got to know some of these identities, otherwise you're going to be pretty much stuck. Now, here's what the arc length says. When we're finding actual arc length from A to B, all we have to do, take the derivative, find the magnitude, and then integrate. So we're doing all of this work first, and hopefully it's setting up for us at least a possible integral. So I'm not going to tell you it's easy all the time, but at least it's going to be possible. So the order of business, take your derivative, find your magnitude, simplify as much as you can before you start to integrate. Does that make sense? You try to integrate something that looks like that. Do you want to integrate something that looks like that? No. No, man, no. So simplify as much as you can. Then when we actually have our arc length is from, right-siders, you tell me the A. What's our A in this case? What's our B? What is the magnitude of the derivative of our vector function, all simplified down? What is it? 5. 5. dt. So we took our derivative, yep. We took our magnitude, yep. We simplified all the way down to 5. The arc length says you go from where you start, where your parameter starts, to where your parameter stops. We integrate that across whatever we simplified to. 5 dt, pretty much the easiest thing that we've ever done in this class. What's the integral of 5 dt? And we're taking that from 0 to 2 pi. How much are we going to get?
10 pi.
That's not a pi. That's a t. Now, what's it mean? That's how long this right here is arc length. This is how long this particular curve is from t equals 0 to 2 pi. Now, if you think about what that is, this right here, do you remember vector? You remember 12.1? That right there is going to give you a circle. Can you see it? It's going to be a circle along the y. That's what that is. Circle along the y is going to be a cylinder. This thing wraps around that cylinder. So we've basically determined how long one rotation around that cylinder is going to be. A chord along the soda can going along the cylinder, soda can, going along that y-axis. That's what we've done right now. Found the length of that wire, if you will. Show hands if you're okay with the idea here. I gotta be honest with you. Most of them are not this easy. Okay, this was a real nice one. We're gonna step it up one time right now. If we have time at the end, I'm gonna come back and we'll do a hard one. We'll do that, okay? So this was probably the easiest I can give you. I'm gonna give you now one I'd probably ask you for on a test. Right? This is the level I would ask. The next level is really probably difficult, but I wanna do it if we have time for it. If not, we'll hang on until next time. Well, let's try at least one more, something that's gonna be very doable at this point for us. So same question. I want to find the, what's this thing? What's that called again?
Vector function.
I want to find the length of this vector function. That's a curve, just a curve through space. I want to find the length of that space curve on that interval. What's the first thing we do, everyone in class right now? What would you do first? Let's try that, all right? For the sake of time, I'm just going to be crushing some derivatives up here. I know you know how to do it. Main things to watch out for here are sign errors, like derivative of cosine, stuff like that. Integral of sine, stuff like that. Sign errors happen. Not simplifying enough happens a lot, and forgetting product rule happens a lot here. So if you don't forget those things, we're generally okay. So first derivative of our vector function, that's our tangent vector, guys. That's a tangent vector at any point. We just use it for our formula. We're going to get derivative of the first times second plus the derivative of the first times a second, but the derivative of cosine is negative sine, so we get that minus. That yields a minus for us. By the way, if you want to switch notation, if you like i's and j's and k's more, do it. It doesn't matter. You're going to be finding magnitude in a minute anyway, right? So it really doesn't matter. When you find magnitude, i's, j's, k's are gone anyway. Who cares? Next one. Derivative of the first times the second plus the first times the derivative of the second. And lastly, man, I love exponentials. Derivative of e to the t, e to the t. Ladies and gentlemen, you guys okay with what I'm talking about so far? You know, before I went any further, I'd probably do what we did when we first started doing derivatives of vector functions that look like this. What's one good thing you would do to this and that? What would you do?
Factor out the e to the t.
I would, because what we're about to do is find magnitude. Magnitude squares stuff, right? It's a lot easier to deal with squares when you've already factored than if you haven't. It gets pretty nasty. So we're going to factor this first. So the way arc length works, arc length says take the derivative. We've done that. Simplify it if you can. We've done that. Now find the magnitude. Head nod if you can find the magnitude of this thing right now. Could you do that? At least set up. Can you set it up for me? I'm going to do on the board. I want you all trying right now to set up the magnitude of this tangent vector. Go for it. So we squared the components. Add them together, take a massive square root, and that's the setup. Man, I really want to know if you made it at least that far. Did you make it that far? Now let's not make some really silly mistakes, okay? What happens when you have e to the t times cosine t minus sine t, and this whole thing's being squared? What pieces get squared? Does the e to the t get squared? Is that going to be e to the t squared? Very good, because we have exponent, you're multiplying that. So let's write it like an intermediate step here. Just make sure we get this right. So I'm going to square the e to the t, that's e to the 2t. I also have this piece squared. We're going to do some work with that. There's no way around that. We have to work with that in just a second. Okay, we've done like a lot of algebra right now. I want to make sure that we're good with it. Left-siders, you guys okay with what we're talking about? I should answer the idea's not that hard. We do a derivative, but a lot of mistakes can happen. We're doing magnitude. It's not that bad. We're just squaring everything and adding it together and making a square root. But a lot of bad things can happen. Are you sure you guys are okay to this point? Show of hands if you are. Right-siders, you're noticing something right now, I hope. What are you noticing here that you probably should do right now? Yeah, if you can do that, goodness, look, this is why we factor stuff, okay? Because when we have something like e to the 2t, and we can factor it out of all of these terms, it becomes this expression that I can take the square root of and pull that out of the square root. You did that in like a trig sum. You do it all the time. Well, it's really nice. Use it here. Here's what I was talking about if you didn't catch it the first time. The way square roots work, they're separable by multiplication. So if I have this factor that I just pulled out of all of my terms, that's great. You can take the square root of e to the 2t. Hey, what's the square root of e to the 2t? What is that?
E to the t.
E to the t. Yeah, question.
There's no 1 in there?
Oh,
Plus
yeah.
1?
If you factor correctly. Leonard's been drinking again. No, I haven't. Yeah, plus 1. Yeah, don't forget that. Sorry, my bad. And the bracket. There we go. Yeah, good catch. I'm glad we didn't make it any further than that. Okay, I saw some of you guys looking back there. Next time, speak up a little sooner, huh? Don't make me look like an idiot, all right? Jeez, goodness gracious. For real, though, are we okay on factoring that guy out? This is what's nice, though. If we can factor out one term and take the square root of it, the square root of e to the 2t, well, okay, so e to the 2t to the 1/2 power, 1/2 of 2t is t. This square root of this is just e to the t. And then we have, well, yeah, you know what? It's really nasty. You're going to have to distribute that. Foil, you're going to have to distribute that and combine some like terms. But hopefully we're going to get some scenarios that work out. A lot of times that happens. We get a lot of sine squareds, cosine squareds. So we're going to do it. It's not going to look that great, but our final product's not going to be that bad. So here we go. There. Now I won't forget the plus 1. All right? All right? Right there. Do you see anything that simplifies on this whole expression?
2 sine 2 cosine.
This whole thing gone. It's gone. Minus 2 of them, plus 2 of them, gone. What else do you see, left-siders? What do you see up there that's also pretty nice? You don't have to whisper. It's okay. You can totally speak up. We're not going to offend anybody. If you answer the question, it's okay. What do you see up there?
Cosine squared plus sine squared.
Cosine squared plus sine squared, how much it give you? What else? Sine squared, cosine squared. What's that give you? I'm not going to forget my other plus one real big, just so I don't forget it. So we have now e to the t times the square root of 1 plus 1 plus 1, square root 3. I'm going to have to work over here to finish off this integral. Notice something. We've literally just done the setup. That's all we've done. We've just done the setup for our integral. The reason why we use this formula and not the whole derivative of the first component squared plus derivative of the second component squared, all that stuff, the reason why we use this is because, firstly, you'll remember better. You just take the derivative, take the magnitude, you're done. Secondly, if you try to do this within an integral, you have more to work with, right? You have an integral flying around every single one of these steps. That sucks. You don't want to do that. So when we're doing this formula, it allows us to simplify first all the way down and then put this into the integral. You guys see the difference there? It's a slight difference, but it's nice. So let's finish this thing off. How arc length works all the time. We go from one value of t to another. We take the magnitude of the derivative of a vector function and we integrate. For us right now, what is our a? What is our a? Where do we start? And where do we end? And what's this nasty thing that we simplified all the way down? Most of our work in this class is going to be algebra at this point. What do we get?
E to the t root.
And?
Square root 3.
But now if you're okay with that so far. Okay. So, is it doable? Yeah, this is the hard part. The integrals typically are not super bad. Sometimes they can get nasty, all right? The next one we're going to deal with, if we have, I don't know if we have time now, but we will do it later. It's going to involve trig sub, a nasty trig sub, or an integration table. But you know all of that stuff, right? Taking Calc 2, you know how to integrate. They can get nasty. I wouldn't give you something that's going to take you 30 minutes to integrate, like on a test. But on homework and things, you can expect that. You expect to do a little bit of work with integrals here, okay? You know how to do that. But let the textbook be your friend here. Use your integration tables. Man, if you remember some of these integrals, use that. This is not, do you know every technique by hand? We're past that, all right? We're way past that. Make it as quick and as efficient as possible when you're doing integrals. So in our case right here, we go, hey, that's a constant. We pull that out in front of the integral. So I'm going to have my square root of 3. Tell you what, I'll take care of this one for you guys, all right? I know, you're welcome. Integral of e to the t, e to the t. Head nod if you're okay with that one so far. Are we done? Practically done. What's the last thing that we would do? Say that again?
Evaluate the interval.
So we have this. Probably a good idea not to just put 0 for zeros, because when we have like e to the 0, that gives us stuff. E to the 0 is how much? Now, what is it? Don't just do the math. What is that? That's the length, I don't even know what that looks like, we could probably figure it out, but that's the length of this curve on that interval. That's how long this space curve is for a given length of time. Should fans feel okay with that one? I would like you to do something for me. I want you to please remember what this remember what this equaled, okay? So for this function, maybe I'll just leave it up here. Because we're going to come back to the same problem in about, I don't know, 20 minutes or so. And we're going to reparameterize this. And I'm going to reparameterize this. So instead of finding the actual arc length, this is the length of that curve for that given amount of time. What I'm going to do is I'm going to use this technique to give that a different parameter. We're going to change from t's into a different parameter, arc length. Now why are we going to do that? That's the next little sub part here. So if we have smooth curves, what smooth means in Calculus 3, these smooth space curves, means that we don't have any gaps, so that they're continuous, and we don't have any sharp points. We call those cusps. Do you remember on like Calculus 1 that you can't take derivatives at sharp points? Because a derivative is basically a limit of the slope from one side to another. If they're not the same slope, the limits don't equal from the left and from the right. Our slope doesn't exist at those cusps. That happens here too. So for smooth curves, we can reparameterize by arc length. Smooth curves, no cusps, sharp points, no gaps. That's what we mean here. Big question. Why? Why would we want to do that? Because there's going to be some good news and some bad news, okay? Why would we want to do it? Number one, you know how vector functions work. Vector functions do this. They say, here's your curve, right? Here's your curve going through space. It's doing all this cool stuff. But what your vector function says is, right now we're at that point, and it points to it, right? Right at this time we're here, and then you're here, and then you're here, and then you're here, and then you're here, and then it's pointing to the points on your curve. Do you remember talking about that with vector functions? So these vectors are just pointing, and the terminal points of the vectors create your curve. That's what's happening. Well, if we reparameterize by arc length, instead of just pointing to where we're at and letting our points create the curve, if we reparameterize by arc length, it allows us to kind of walk the curve. To say, hey, we're going this way for this amount of time, or this length, and we're curving. We're actually walking the curve instead of just pointing to it. It's a more natural way to think about it. That's one way. That's one reason. So for one reason, it allows us basically to, I'm going to say, walk the curve. Number two, the real reason. 2 and 3 are the real reason. You don't get 3 till later. Number two, some formulas are way easier if we reparameterize. If we do that. If we reparameterize by arc length, some formulas become way easier. In fact, we do some of this in our work with vector fields. When we get to chapter 15, we're going to be doing some of this. Some of the formulas are defined in terms of arc length. We're going to use that. So these are the two ideas on why we would want to do this. How? Well, we're going to talk about that in a second. There is a third reason. You're going to get it after our first or second example. Number 3, wait for it. Wait for it. So, do you understand the why? Why we get to travel the curve, basically walk the curve. 2, well, some formulas become way easier. Part of 2 is some formulas are even possible when we get to like chapter 15. Some of these things are defined in terms of arc length. Number 3, we're going to wait for it till after our first example. There's good news and there's bad news. The good news, you already know how to do this. We've literally just found arc length. It's the same thing. Remember how I talked about if we're going between two values, you get the length, and if we're not, we get the arc length function. Remember talking about that? We've already practically done it. That's the good news. The bad news is it pretty much always sucks to do. All right? It's not fun. You have a lot of simplification. All this stuff happens. You go, I don't want to do this. It's typically not that fun. So I'm going to show you how to do this with yeah, maybe I'll do that with this example. We'll wrap this thing up, and then we'll. No, I got to see if an easier one before we do that, because I want you to really get it. So we're going to do one fresh example, then we'll come back to this one, wrap that up, and that will be the 2 that we're going to reparameterize. So are you ready for our easier of the 2 examples? Okay. Anybody out there who wants to impress me right now, tell me what that is. Impressed. Did you recognize it? If you put x equals, y equals, and z equals, you got a very basic line. It's just a line, parametric equation of a line. That's all it is. That's a line that actually starts somewhere, though. We're starting at t equals 0, we're going positive. So this is a line with a direction to it, of course. But we're going to reparameterize this. I'm going to give you the steps, and the reason why I want to do this one because it's fairly easy to do. We're going to get some nice constants, and it's going to be pretty quick. So here's the idea. Number 1, we're going to find the arc length function. We can't find the arc length. Notice that. Can you find the length of that line? Infinity. Done. Because it starts at 0, it goes forever. Unless I stop, I can't find the arc length. What I can do is find the arc length function. That's number 1. Not L, we're looking for S of t. Good news, it's literally done the same way. So what I want you to do right now, I'm going to give you about 30 seconds, all right? I want you to find the arc, oh man, the first thing that you need to find the arc length function. So you remember what arc length is. It's the integral of the magnitude of the derivative of our vector function. So what's the first thing you do here? It's like being back in Calc 1, right? If you don't know the answer, say derivative, you're probably right. Find the derivative, find the magnitude, go. I got I plus 2j plus 3k. Did we all get the same thing? Yes, no? You guys over here? Perfect. Now what's the next thing before we do our integral? We're going to do what? Magnitude takes the components, squares them, adds them, square roots them. It's just like finding the magnitude of any other vector that we do. get the square root of 14. Did you get the square root of 14? What's the next thing that we would do? What do you think?
Integral.
We're going to integrate. Now, there's something that I need to show you here. We're not finding L. We're finding the arc length function. It's still an integral. It's still going to be this mess of junk. So we have S of t equals the integral of r, magnitude of r, d. But there's a, listen, in order that we don't get mixed up between all of the t's floating around, we need to get a function of t out of this thing. But if you remember back to the fundamental theorem of calculus, we're going to use this idea. They use this dummy variable like a u. So any place you see a t, just replace it with a u, du. And here's how this works. We're going to go from a to t. This a, that a is where your t starts. You're going to have a starting point here. Okay, it's where your t starts. T, you leave the t. That's your parameter. That's telling you I can go as far as I want. It's not finding a specific arc length. It's finding a formula for arc length. Verify something for me. If I do this, if I take the derivative with respect to u, I'm going to get a whole bunch of u's, correct? If I then plug in t, notice how the u's get replaced with t's? That's why we call it a dummy variable, because it's just kind of holding the spot. If we had t's floating around here, and we had t's floating around here, and we did the integral, and then tried plugging in t's for t's, it's going to look weird. Does that make sense to you? It's going to look really strange. So we hold this variable open with u's. So basically, if your magnitude still has t's in it, replace it with u's. Then do the integral. The t's are going to work itself out anyway. So replace the t's right here. It doesn't have any. I'm giving you an easy one. But here, did you see that? We're going to... That one. We're going to replace that t with a u so that this integral actually works. Does that make sense to you? Are you sure? Because I don't want to just say, does it make sense to you? And you're like, yeah, just shut up, Hunter. Just keep on going. Does it? I say that a lot too. I know sometimes it's redundant, so I'm going to break it up here. For real, do you understand the dummy variable idea?
Yeah.
Do you see that the t's are going to be in there at some point? We're going to get it. So a is where the t begins, 0 in this case. A is where the t begins. T, you leave that t. It's how we get a function of t at the very end. Other than that, we're going to replace every t with u. I guess it really is a u sub. It really is. So let's give it a try. We're no longer finding arc length. We literally can't. We're starting at one point. We're going forever. So let's see. What goes down here? Keep in mind that this number is where your t starts. What is it?
0.
And where's it end? It doesn't. That's why we have the t. This is going to give us our t back. What goes in here, please?
14.
The same thing that goes in any arc length idea. It's the derivative, the magnitude of the derivative of your vector function, in this case, square root of 14. And then do this. It's du. It's not dt because we're going to have to plug in the t in just a minute. And not if you're all right with what I'm talking about. That's what has to happen. This technically there's no u's there, but if it had t's, we'd replace them with u's so that our integral works. You know how integration works. You get a match of variables up. So here, everybody, what's the integral of the square root of 14 to u?
Root 14. Square root of 14.
U. And then where are we going to go from?
0 to 0.
0 to where?
T.
If you're wondering, like, why don't we just take the freaking integral anyway and just put a t there? Well, because sometimes that 0 changes stuff. Here it doesn't, because you have t minus 0. Yeah, it's just t. But if we had, I don't know, like e to the t, is the 0 going to be relevant there? Yeah, you better believe it. So it's going to change stuff. So we do actually have to do it this way. In our case, we have, we'll move over here. Oh yeah, sorry. square root 14t. You plug in the t minus 0, you just get t. Head and if you're okay with that one. Now here's how this works. This is the formula. Please listen, I'm only said it a couple times, okay? This is the formula for arc length. Do you believe me? This is how arc length is found for this particular curve line right here. This is the length for any value of t starting from 0 and ending at t. Does that make sense? So you want to say, hey, what's the length up to t equals 5? Plug in 5. You have the arc length. What's the arc length up to 7? In 7, you have the arc length. It starts at 0 to 7. Does that make sense? Now, if we reparameterize, what that means is, well, let me ask you, what's the current parameter right here? That's not a big shocker. Everybody, what's the parameter here? Can you solve this for t? If you do, let's drop this, okay? If you solve this for t, s over square root of 14 equals t. You with me? That gives you a substitution. If you substitute this in for every t over here, you now reparameterize this curve, this line, in terms of its arc length. So instead of just having values of t, now you have for a distance, this length of a curve, how far you're traveling along this line. You're literally traveling along this line right now. So if we do this, if we substitute this in, this now becomes this. Instead of r of t, I now have r of s. It's now in terms of arc length. Instead of 1 plus t, no. I don't want t's anymore. I don't want that parameter. I want arc length. I have 1 plus, how much is t equal to? Come on, quickly. What is it?
That's root 14.
Plus, instead of 1 plus 2t, I have 1 plus 2s over square root of 14. Instead of 3t, I have 3s over square root of 14. Okay. There's one more thing. Look here. Look here. Where does the t start? 0. Plug in 0 here. Where's the s going to start? You plug in 0 for t, does it still give you 0? If you plug in numbers bigger than t, like 1, 2, 3, 4, does this also create positive numbers bigger than 0? So then our interval, instead of t greater than 0, it's s greater than 0, because when I plug in t equals 0, I still get s starts at 0, and it goes positive just like t goes positive. Show of hands if you understand the concept here. That's reparameterization. Now, here's the number 3. I'm going to fill this in for you right now. The third reason, the most important reason why we do this. If you take a derivative of a vector function that has been reparameterized by arc length, listen carefully. If you take a derivative of a vector function that's been reparameterized by arc length, its magnitude will always be 1. Do you remember the name of the thing that we had that was a tangent vector that had a magnitude of 1? What was that called? Unit tangent. That will always give you a unit tangent vector. Is it important? Yeah, you better believe it. We need it for things like curvature. We need it for things like osculating plane, osculating circle. We need it for torsion. We need it for these pieces. So if we reparameterize by arc length and we take the derivative, it's always there. So this, a vector function parameterized by arc length, the derivative of that function will always have a magnitude of 1. In other words, it's the unit tangent. And the tangent, we're going to discover this throughout the course of this chapter, is really important for us for this chapter. That's the whole shebang. Do you know right now how to find just the basic arc length? Say, find the arc length between these two numbers. Would you know how to do it? Explain in your own words right now. What's your first step? What would you do? Derivative. And then what? Magnitude. And then what? Done. Derivative, magnitude, integrate. How would you reparameterize? Same stuff. Except when you get down to the integrate part, you have u's instead of t's, and you go from like 0, your a, wherever your t starts, to t. You get a function of t, and you solve for t. We're going to do that next time with this example, so I'm not going to redo this, okay? I'm going to say, hey, remember the vector function? It was like this, and then we had the magnitude, it was like that. You remember that? We're going to go right from here. Your next step here is going to be this. We're going to do that. We're going to solve for t. I'm going to show you how it works, and then we'll be about done. Did today make sense for you as far as this goes? Okay, cool. Okay, so we finally get to wrap up this problem. We were talking about how to reparameterize by arc length, and what the idea was our parameter right now is t. What if we reparameterize by arc length? And you go, well, firstly, why? One big reason why, and I mentioned it earlier, there was really like 3 reasons, but one of the big reasons was this. If you take a derivative of a vector function, everyone in class right now, what's the derivative of the vector function? What's it giving you? It's a tangent vector. If you reparameterize by arc length, the magnitude of that tangent vector is 1. It's always 1. They're like, okay, who cares? That's really important for some of the other things we're doing in here. So that's why we learn this technique. Now, I gotta be honest, we don't use it very often, but it's there. It's there if you need it. So and that's what we're gonna do this example. We're gonna wrap it up and then move on into our TNB frames. So what we did last time was from a previous example, we took the derivative, we found the magnitude, we did a whole lot of simplification, we worked it out to this thing. Are you with me on what I'm talking about? We also know this. We know that arc length, don't write this one down, I'm going to change it just slightly, write the next thing I write down, okay? So I'm going to change it a little bit. Arc length does this. Arc length says go from A to B of the magnitude of the derivative of our tangent vector dt. That's what arc length does. If you're actually finding the length of something, do you remember talking about that? Going from like 0 to pi, going from whatever, it would find the actual length. If we're trying to find the arc length function, which is what's going to allow us to reparameterize this curve in terms of not t, but s in terms of arc length, then this changes not L, it changes to s of t, the arc length function. This doesn't change. This is still where you start. So this in our case right here is 0, but this changes. This says, well, now I'm not ending. I'm not stopping at B. In fact, I'm not stopping at all. I'm going for all t. So we have a starting spot. We don't have an ending spot. Now, in order to kind of mitigate some confusion here, instead of having t, and we talked about it last time, I said it, but if you're going to integrate this dt and then go plugging t's into t's, it can get really confusing. Does that make sense? So what we do instead, it's a dummy variable, it's literally a u sub. It says, you know what, let's just replace any t's that are here with u's, integrate du, write that down, integrate du, and then when we plug in our t's, later, when we evaluate this thing, then we'll get our function with respect to t, or sorry, in terms of t. Does that make sense to you? So let's see. Do we already have the derivative of our vector function and have found the magnitude to it? Yeah, that's this thing right here. So if I'm going to try to set up the arc length function, it's going to be an integral. Right-siders, you get the first one. Where is this going to start? Keep in mind it starts the same place that t starts. Where's it going to start?
0.
Where's it going to end? It's not. This is just so that we can put our variable in there. It's not ending. It's just starting at 0, not ending. It's allowing us to plug in whatever variable I want later. That's the whole point. What goes, be careful left-siders, what goes here? What's in here? You don't have to whisper it, man. I can't even hear you. Goodness. Square root of 3. E to the what? The u. Yeah. Any place you see the t, if you have t's, any place you see the t, just put a u. It's a dummy variable, and when we plug the t in later, it takes care of everything for us. Then we integrate du. That's the idea. Show of hands feel okay with this idea. Now let's go ahead and let's do it. Is this a hard integral to actually do? That's pretty darn easy. So square root of 3, everybody in class right now, integral of e to the u du, come on. And then we evaluate from where to where, please?
0.
What's the first thing you plug in, the 0 or the t? You know what, it's 0, right? I don't even have to plug it in. True or false?
False.
That's what that 0 is there for. It's an important concept. When we're starting someplace, you're actually getting this formula. I don't want you just to do this stuff. I want you to understand it. Please listen. What we've done now is found not a specific arc length, a formula for arc length. Look, if I wanted to go from 0 to 7, all I have to do is plug in 7. Done. Look at the integral. It would work for you. 0 to 7, you'd have t's here. You just plug in 7. It's the same exact thing. So you're finding a formula for the arc length. Show of hands feel okay with that one. So it's only slightly different than L in that instead of a number, I have a t. That's all that's happening. Yeah, we use a u. It looks a little weird. It's a dummy variable that allows you to plug in the t somewhere. That's the idea. But it is literally just a formula for arc length, giving us a length of this space curve between 0 and any value that I want. If I wanted to start at a different value, yes, you'd have to start at a different value. Does that make sense to you? So yeah, okay. Now we'll simplify it just a little bit. But here's the point. If you have a formula for arc length that's based on t's, you can solve this formula for t. That allows you to take whatever t is equal to and substitute it back into your original vector function, and that is what reparameterization by arc length means. So let's give it a try. Can you solve that for t? It's going to be a little nasty. I'm going to give you a little piece of advice. Number 1, you don't need the s of t. So just ignore the of t, just write the s. So instead of s of t, I'm just writing s, and the s becomes my new parameter. Next up. When you solve this, of course, you'll be dividing by the square root of 3. Do you guys see what I'm talking about? Dividing and rationalize, you'll get root 3 over 3 s. So we divided, but then we rationalized, root 3 over 3. Still okay so far? I know it's just algebra, but the just algebra, man, that's the hard part. What's the next thing y'all would do? What would you do? For sure. If we add 1, we get this. I'm switching sides here, but we get that. Quick hit now if you're okay. Let me give you a piece of advice. Stop what you're doing, just check this out for a second. If you have any pieces of your vector function that are e to the t, oh my gosh, use this. So check this out. You see all the e to the t, e to the t, e to the t. Since we've solved for e to the t, this is what we would use to put here and here and here. Does that make sense? If you have other t's, yeah, you got to keep going. Then you would, oh yeah, by the way, how do you get rid of the e to the t? How do you do that? Take natural log on both sides. So ln on both sides would give you natural log both sides gives us this. So we kind of a twofer. We can substitute in for e to the t. We can also substitute in for t. I would like you to verify that if you put this here, e to the ln, gone. You get square root of 3 over 3s plus 1. You get exactly the same thing. So make it nicer. If you have e to the t's, use this. If you have just straight up t's, you got to use that. This is going to look just completely nasty, but I'm going to write this out for you. I'm going to show you what the reparameterization is going to look like. So our new vector function, instead of being in terms of t, which is the original parameter, it's in terms of s. It'll be arc length now. Arc length reparameterization. E to the t, use this guy. Times cosine t, there's no getting away from this guy. And that's just the I. Do you see where it's coming from, though? Here's your e to the t, here's your cosine t. That's where this stuff is coming from. Sine, basically the same thing with just a sine. And then lastly, you have just this piece. So I'm getting jammed up against the side there. Square root of 3 over 3s plus 1k. That looks a whole lot better, right? Yeah, now, again, don't just do math for the sake of math. Why in the world are we doing this? There was 3 reasons. 1, instead of just pointing to points on your curve, it allows us to imagine walking it by arc length. 2, it makes some formulas nicer. This one, no, but some formulas. 3, the most important one. The most important one. Now, it would not be nice to do this here, but check this out. You have your attention. If you take the derivative of this, what's a derivative of a vector function, everybody? What is it? If you take the derivative of this one, you're right. If you take the derivative of this one, you're right, but it's also the unit tangent vector. That's the point. Because here, if you wanted to find the unit tangent, do you remember talking about that earlier? You got to find the derivative, then you have to find the magnitude. It wasn't easy. And then you have to divide them. Make sense? And they all have t's in there floating around. So you have a choice. Do you want to find a derivative? Do you want to find the magnitude of said derivative and then divide them? Or do you want to reparameterize by arc length and then do a derivative? Either one would give you the unit tangent. There's not a good answer here because they're both hard. There's no good way to do it. But you have a choice. I'm just trying to explain to you why we do it. Why we do it is because the derivative of this is still a tangent vector, but it is automatically the unit tangent vector. And that's the idea. Show of hands if you understand that idea. Okay.
That's pretty bad.
All right, so we got this one last example. We're going to find arc length for, so I know I didn't write it, but I want to find arc length, not the arc length function. This one would be really nasty to find the arc length function for, and I'll show you where, when we get there, where you would find arc length function. But I want to find actual arc length for this thing. So I want you to do most of it, though. I want to start off with the first step for finding arc length. If you don't remember what the formula is, remember that arc length would be our L, integral from A to B of, what's in there? Do you remember? It's a magnitude of that. Now, let's go about making it. What's your first step? If I give you this problem, I'm not going to give this problem on test, it's way too long, all right? But it's really, really good practice for us, so let's start there. What's your first step in determining the arc length, the actual arc length from A to B? on this problem, what would you do? Let's do the derivative. Go for it. When you're doing, oh man, I hope that you actually see the product rule. Do you guys see the product rule? Yes. When you're actually doing the product rule, keep it in parentheses. All right, please do that, because it's going to be one component with the J, and then one big, huge component with the K. Make sure you keep it in parentheses. If you can skip steps with derivatives and still get it right, fine, fine. But make sure it sucks, right? To be able to do a huge long problem and mess up the first sign. That's awful. It happens all the time. Don't do that. Don't do that. Did you all get that, at least that derivative? Yes, no? Okay, so we're building arc length. What's the next step? What would you do?
Magnitude.
I want you to set up the magnitude right now. Go for it. So to find arc length, yeah, we're going to build this. I know what A and B is, that's pretty easy. But I take derivative, then we find magnitude of derivative, and it's got to have a lot of t's in it. It's got to be of the function. So set up magnitude. Tell me in your own words how you find magnitude of pretty much any vector or any vector function. What do you do?
Square.
Square it? Adam? Good. Should I ever have i's and j's and k's inside of my magnitude?
No.
Perfect. You sound like my little math robots. I love it.
No.
Professor, I know you should not. Let's try that every time. It'd be really creepy. You'd be like, what are these kids doing? Did you make it that far at least? Now there's a lot of stuff that we're going to have to do to simplify this. That's really nice. We're just going to put 4t squared, no problem. When you have things like this, listen, don't write out all of this stuff all the time. Just take these two pieces off. What happens a lot when you have derivatives of things, components that have both sines and cosines with t's in front of them, e to the t in front of them, you're going to get a lot of product rule, which means that you're going to get a lot of distribution when you square stuff, which means you're going to get a lot of cosine squared, you're going to get a lot of sine squared, you get a lot of sine squared, you get a lot of cosine squared. Those things almost always simplify, at least some parts of it. So take both these pieces off right now. I want you to distribute, put a plus sign, and distribute, and see what happens. Go for it. I'll give you about 30 seconds to do that. Man, is it really curving up there? Yes, looks like I'm drinking again in class. Shoot, sorry, my bad. Can't write straight on the board, never nailed to. I'm really not. Check me for my mistakes, I make them too. Did you get the same thing I got? Yeah. Yep. Okay, cool. What happens here? What happens in our problem? Do you see anything that simplifies?
2t sine t cosine t.
This stuff is gone. Love that. So what we're left with, if I'm going, I'd like to reorder this if you don't mind. I got cosine squared t, I got plus sine squared t. I like that. I also have t squared sine squared t, t squared cosine squared t. What I'm going to do here, what would you do here? Let me ask you that. What would you do with t squared sine squared t and t squared cosine squared t? What would you do?
Factor.
Yeah. The obvious factor. Here's what happens when we start simplifying too much and going too fast. We start losing numbers. We start doing things like, hey, how much is this right here?
1.
It's 1, but that 1 matters because we're adding it. That 1's going to be there. Plus, and this is t squared. How much is all this stuff?
1.
Times 1. So this t squared is also there. So this is 1. This is also being multiplied by 1. So if we rewrite this magnitude, we still have this. We got 4t squared plus this whole thing works down to 1 plus t squared. Can we make it even better?
Combine.
Yeah, let's combine some like terms. I'd like just a show of hands if you feel okay with the algebra behind it. Show of hands if you do. Is the calculus super hard? No, but the magnitude of these things, man, it can get really nasty. Now, here's the deal. Right now, we get the magnitude of the derivative of the vector function. Where's that go? What do we do with it?
The integral. First.
All I hear is what do you do with it?
Integrate.
Integrate. From where to where?
0 to t.
So right now, we're here right now. So our arc length is integral from 0 to 1 of this thing. You see, when we took the derivative, that was great. When we took the magnitude, that's even better. Once we get the simplified version, this is why we do not do it in here. It's why we have this specific formula, not the f prime plus g prime plus h prime squared square root of, because you'd be doing this all in an integral. That's crazy, man. You're writing too much. So figure out the magnitude of the derivative of the vector function first, simplify it as much as you can, and then at least this looks a little bit better when you try to integrate it. Do you guys see the technique here? That's why we have the formula like this, the way that we do it. Is it really different? Not really different, but the manner in which you accomplish your tasks is slightly different, makes it nicer. I'd like a show of hands who feel okay with this so far. Now, I'm going to tell you something about integrals in this class. In Calc 2, I would make you show all of your work. In Calc 2, I would want to see probably a trig sub and that you know what you're doing. Because right now, a u sub doesn't work, integration by parts, heck no. It's got a square root with 2 squares in there, or you're going to force it to be 2 squares in there. That's a trig sub. If you can use a table for that, do it. Do it. You can use a table right here. It's literally in most integration tables. From right here, just do it. If you don't have a table, or you don't know how to do it, or you don't know what I'm talking about, then you got to go fall back on those integration techniques. I'm going to show you how to do that up to a certain point, and then for sure after that point we'd be using a table, because there's no way you're going to want to do the rest of it. You guys with me on what I'm talking about here? So let's draw ourselves the triangle. If I really want to think about that as a trig sub, I'd be thinking square root of 5t squared plus 1 squared. That's what I'd be thinking about. Now, if you were in my Calc 2 class, I always told you to think about this as a side of a triangle. Don't rely on formulas. It's a really bad way to even learn trig sub. What side of a triangle would be a plus square inside a square root? What side would that be? Say what? Hypotenuse. Yeah, for sure. Always draw your triangle in the same orientation. It's a really good idea. So this would have to be the hypotenuse. Now, when I taught you in Calc 2, I said that what we want is one of 3 trig functions. We want sine, or tangent, or secant. And we also want it so that it's variable over constant. We have to have that. So where am I going to put the, by the way, you know this if you've seen trig sub before, you know that this piece inside the square is one side, and this one is also one side of this right triangle. Where would the square root of 5t go? Would it be here or here? Keep in mind I want sine or tangent or secant, but I want to have a constant on the denominator. So where would the square root of 5t go? For sure. And that would be 1. What trig function is going to work for us? The sine, the tangent, or the secant? Secant would give us this over 1. That's okay. I don't really want that much. I want to make it nicer. I don't want a freaking square root in there, okay? So what's going to give us no square root around variables is what I'm talking about. No square root around variables, and also have 1 on a denominator. What's going to be? It's going to be tangent. Sine would do this over this? No. Tangent would do this over this? Yeah. That's what we want. So tangent equals square root of 5t over 1. I don't even need the 1. It's just square root of 5t. With me on that one so far. That's how trig sub works. If you need refresher, that's 7.3, 7.2 in Calculus 2. So if you don't want a refresher on that one, you go back and watch it. I would personally just use a table, but I'm doing the courtesy here. If you don't have the table in front of you, that we have another technique, okay? After that, with any trig sub, you solve for that variable. You'd be dividing by the square root of 5. If you divide by square root of 5 and rationalize, we get t equals square root of 5 over 5 tan theta. Are you still okay with what I'm talking about? Now what? What do you do next? That's right. Before we substitute, we have to substitute for this dt as well. This has got to change. That's where this comes from. All the people who forget to write this all the time, you go, oh yeah, it doesn't matter. It matters. It matters. Because when you change variables, you have to change this, what you're integrating with respect to as well. So taking a derivative of both sides, we get square root of 5 over 5. Everyone in the room says derivative of tangent is
Square root of theta d theta.
yes. And that gives us a substitution. By the way, you can change bounds, but it's not wise with trig sub. The reason, well, you can change bounds. I'm not going to because I'm going to show you how to convert back to our original parameter, but you can. The reason why you might want to practice not doing that is because if you have to reparameterize by arc length, there's no bounds to change. And you go, how do I do this? Well, you didn't practice that. Does that make sense to you? So we're going to practice not changing bounds with this. What we do is 0 to 1. By the way, you can be smart about your substitutions. Hey, if I had the square root of 5t, I know that whole thing, the square root of 5t, is just tangent. I don't need to solve it all the way down to t and then plug that in, then unrationalize, then simplify the square. That's crazy. Okay, I don't need to do that. This piece right here is tan theta. So I have tan squared theta plus 1. I also know that the dt is right here. Hey, left-siders, what's tan squared plus 1? What's that give you?
6 squared.
That's why we choose these things, so they work out pretty nice. So they're identities. Next step, right-siders, come on, quickly. What are you gonna do? Okay, left-siders. No one's over here anyway, whatever. Can't tell. You get another chance, right-siders. What do you do? Go on. What do you do with the root 5 over 5? What would you do with that? For sure. How much would it give you all together inside as your integrand? What would you get? Yeah, that's exactly right. Show of hands if you're okay with what we're talking about. It's just Calc 2. Calc 2's killer if you don't know how to do trig sub. You don't know. Now here's the deal. Do you know how to do the integral of secant cubed? It's not an easy one. This is one of those ones where you split off the secant. You do secant squared is 1 plus tan squared again, and then you do a whole, no, actually you do a secant times secant squared and you do by parts. And you go, okay, integration by parts, u is secant, integral, v is integral of secant squared, and you go blah, 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 blah. It's one of those add backs that you add to the other side and you divide. Do you remember doing those in Calc 2? You can look it up. It sucks. I actually do this, and I do it to the 5th power, I think, on the video, but the 3rd power is in there. So if you want to check that out, go for it. You know what I do? Table. Man, that's an integration table. It's right there. It's already done for you. For goodness sakes, wherever you can use a table to do it, you could literally have done it right here. This is in the integration table on most textbooks. This is in every single textbook ever that's in there. Use it. Use that. And I use it here. I don't remember them. I can't remember all those. So the integral of secant cubed theta yeah, we get so wrapped up in magnitudes. It's not a magnitude, okay? That's absolute value. So, I know, but man, maybe a quick 10-second recap. The idea is easy, but the doing it's hard, man. So we have vector function. We can find the length of any vector function, a space curve between any 2 points, as long as we can find the derivative, find the magnitude, and integrate from this point to this point. That's exactly what we've done. We've made it down to this far. We've just accomplished the integral. Now, a question. Do you get to plug in 0 and 1 right now? What variables are this 0 and 1 in terms of?
T.
And this is theta. So you've got to be able to go back to the t. Now, the reason why I didn't change right here, the reason why we didn't change bounds here, when you're doing this for reparameterization by arc length, you got to be able to solve for the t. Let me show you when that would happen, okay? So what we're going to do right now is change back to t's. It's why you draw the triangle. It's how to use that triangle that lets you change back. So going over here, we got L equals square root of 5 over 5. No problem. We got a 1/2. That's pretty obvious. Secant theta, use your triangle. It's the same theta here as it is here. So secant is the reciprocal of cosine. If cosine does this over this, secant does this over this. So it's a square root of that plus, hey, you know what? You actually have tan theta. It's right there. You don't have to find it from your triangle. It's literally what you substituted. So it's square root of 5t. And then we have the same two things in here, but they're added together. Oh, you know what? Little mistake. It's a pretty common mistake, letting our square root float too far over. It happens all the time. You'll see me put a little tail here when it doesn't go over that way. I make a little note to myself that I don't want it floating over pieces where it shouldn't be. Now that it's in terms of t, stop. Just pause for a second. This right here, if you don't go from A to B, if you're reparameterizing and you're starting, say, at 0 or something, that would be your arc length function. Okay, that would be your arc length function. What you would do now, and you might have more to it, because if we were going from 0, well, you'd be evaluating from 0 to t right here. You'd have a whole bunch of u's. Does that make sense? You'd have a whole bunch of u's. You'd be going from 0 to t. You'd plug in all the t's. You'd plug in all the zeros for the u's. You'd figure out what happens, and then you'd have to solve this thing for t to reparameterize it. Does that make sense? That's why we're not doing it, okay? Because I don't even know if it's possible. It doesn't even look possible to do. But that's the process where you change. So if you're reparameterizing, solve for t. If you're not, after you plug in your a to your t. If you're not, thank goodness we're not, this is where we get to plug in 0 to 1. I'd like you just to try it right now. Go ahead and put those in appropriately, and then we'll call it good on our section here. Put it in 0, that's a 0. But put it in 0 here, that's a 0. Put it in 0 here, that's a 1. Square root of 1 is 1. Absolute value of 1 is 1. Ln of 1 is 0. So that 0 makes all of this stuff 0. That's pretty nice. If you were reparameterizing, you're doing that one thing with the parameter and changing everything. If you're doing that, you'd be solving for t now. That is nasty. That's really nasty. But let me ask you a question. Is it a number?
Yes.
Is it a number?
Yes.
What's it mean?
Sorry.
That's the length of that curve, that vector function that we started with. I had to erase it. That's the length of that vector function from time equals 0 to time equals 1. That's exactly what we're finding. Are you understanding the concepts? I really need to check for your understanding here to make sure that I've explained this well enough for you guys to get it. That's a pretty difficult problem. I think you can agree, right? There's a ton going on here. Can you follow it? Did you follow it down all the way? That's great. I'm proud of you. That's fantastic. Are there any comments or questions about how arc length works and how arc length parameterization works? Because I want to make sure I clear up anything. Do you guys have any questions on that at all? No? Okay. Again, why would we ever do arc length reparameterization? Why? Why would we do that?
It's easier.
What's the derivative of a vector function that has been reparameterized in terms of arc length? What's the magnitude of the derivative of that function? Good, because it's the unit tangent. That's essentially why it makes our work easier later. Do we actually do it? Yes, sometimes, but it's really hard. So a lot of times we do the workaround. Okay, that's the idea. I can't stop this. We have a new idea. Now, usually, when we think about Calculus 3, we think about our IJK frame of reference. Think XYZ. We have our X, we got our Y, we got our Z. That right-hand coordinate system gives you the XYZ. And that's normally how we think of this stuff. That's great. That's great. If you're standing at the origin, if you're the one standing at the origin and you're not moving and you're just watching stuff, we can describe everything. We say, oh, here's this, think of a really cool airplane, okay? We got this really cool airplane going through space, awesome, and we can describe that motion, but only in our perspective, only compared to where we are standing. As soon as I move, does that work anymore? Does that frame of reference, we're going to call it the IJK, does that frame of reference work for anybody else? No. Does that frame of reference, more importantly, work for the pilot? Think about the pilot. When that pilot is out here, I was going to bring my Imperial shuttle because it has a perfect thing, but I forgot it, and it's really little, so I didn't. It was Legos. I didn't bring it. I like Legos. Buy me Legos. My birthday. It's coming up. So anyway, if you imagine the pilot, so if you were standing at the origin, you got IJK, and you can describe his motion pretty well. He's just flying through the sky doing an air show. Do you guys see the airplane? Can you even see that? Okay, cool. Well, imagine his perspective. He's got a much different perspective, and a much cooler one, because he's flying all around, right? Imagine his perspective. At every moment in time, his frame of reference is changing. He still has this three-dimensional frame of reference, but as he's moving around, this thing it's changing with him. His frame of reference is changing in respect to how he's moving. Does that make sense? Or a particle. We often think particle. That's what Frenet-Serret, that's what that frame, these guys are describing the motion of a particle traveling along a curve. We call it TNB because I'm not French. So I don't know how to say it very well. I'm pretty sure it's Frenet-Serret. I don't know. Do you speak French? I'm more Spanish myself, but Frenet-Serret is how I believe, correct me if I'm wrong, I don't know, how that's said. I'm just a stupid American, so I don't know how to say Frenchy words all that great. Frenchy people should help me out. So anyway, we call them TNB frames. They mean the same thing. That moving frame of reference, that moving it's not IJK anymore because IJK is solid, but that moving frame of reference with a particle is what a TNB frame describes. Now, we don't know what TNB even means, but we're about to think about that. So do you understand the idea? Do you understand the idea that if we want to describe the frame of reference for something that is moving, that frame of reference is changing at every single point. It is not static. It is a dynamic frame of reference. Head nod if you understand that concept. And it's not the IJK frame because that is set in space. That's like at one point doesn't move. So this is moving through space and the frame of reference is changing at every point. So at every single point, the TNB frame gives us these things. At every point, the TNB frame gives us the unit vectors that particle is. Now, I want you to understand why we call them unit vectors. At the origin, our frame is the IJK frame. I is unit vector, J is unit vector, K is unit vector. It gives us a frame of reference, but only about the origin. Does that make sense? So we also want this moving frame to be unit vectors. What the TNB frame gives us are this moving frame of reference, similar to IJK, but we have to define them differently, because at every single point we're going to have a different I, J, and K. We're going to have a different heading, a different way that we're turning, and a different way that we're twisting. How we describe it is with the T. Wait a minute. We've talked about the T before. What's the T stand for? What's that even mean?
Unit tangent.
It's the unit tangent. So at every point, the TNB frame describes for us the unit vectors. Well, the unit tangent. The unit, what do you think the N stands for? Norm. What would be perpendicular to the tangent? Because we want this mutually orthogonal system, just like IJK. So if we have the tangent, we also want something that's perpendicular, the normal. And then the B. The B's like, what's the B? The B is called the binormal. Here's what these ideas represent as we're considering this airplane, or think particle if you want to think smaller. As we're considering this airplane, what the T stands for. So you're in the airplane, okay? What the T stands for is where that plane is pointing. It's where that plane is heading at the instant of time. Is it going to change later? Yep. But at that moment in time, it's where that particle is heading, or where the plane is pointing. The nose of the plane is pointing. That's what the T represents. I don't know if you understand the concept there. Just a tangent. It's giving us instantaneous vector right there, where it's heading right in the moment of time. Now I'm using a really specific word. If I say unit, what's a unit vector doing? It's the direction. So this frame of reference, since they're unit vectors, are just giving us the direction. The T gives us the direction of where the plane is pointing, or where the particle is headed. It's where the direction the particle is heading. You can think, if you want to write a little note here, it's where the nose of the plane, I'll write it later, but it's where the nose of the airplane would be pointing. The normal. The normal is how the plane is turning. Turning doesn't mean this. How airplanes turn, if you've ever seen them actually fly, what they do in order to turn is they turn like that. Have you ever seen that? They bevel over, well, they can't over, and then they turn this way. It's almost, and I want you to think that this is the only, I know that there's this little flap back here that can make them do this subtly. I know that. But let's pretend the only way they turn is if they are turning perpendicular to the tangent. And that would describe for you what the normal is talking about. So the normal, the unit normal, that's what this big N means. The unit normal is where the plane is turning, or where the particle is turning, or direction. Where the particle... Did I spell particle wrong?
Yeah.
Typical math teacher. That's silly, Leonard. Why don't you correct me? Oh yeah, you didn't want to anger the Leonard. I get it. All right, but you can correct me. That's okay. Be fine with that. Particle. You ever heard of particles before? Losers. Just kidding. Jeez. The binormal. The binormal is this. Imagine doing this. Imagine you're in the airplane, okay? You don't even look at the airplane. Look at my cool airplane. If you're going straight forward and you're doing this, is your heading changing? No. Are you actually turning? No. What are you doing?
Rotating.
You're rotating or twisting. That is what the binormal describes. So the binormal describes how this particle is twisting. That's what this is doing. I'd like to draw you just a little picture here about what's going on. So we typically stand right here, we watch all this stuff going around, and we're watching a really cool airplane show. So this thing's coming out here, it's always above the, well, hopefully it's above the XY plane, otherwise it's crashing. So what's going on? If this has a certain orientation to it, it's traveling through space. What are airplanes doing? This guy's coming up, maybe it's banking down, turning up, turning around, and going back the other way. At every moment in time, this airplane has a specific heading, has a specific direction it's turning, has a specific way that it's twisting. That is what the TNB frame describes. So if I wanted to overlay the TNB frame, I'm going to try to do it right here. At every single point, here's what's going on. We have this tangent. The way the plane is, at that moment, heading, the direction where the particle is heading at that moment. We have the normal. That's perpendicular to the t, the unit tangent. It's where the plane is turning. And then we have this other one. This other one is the binormal. That word binormal, the bi like a bicycle, or well, other things, biplane, has two. It's binormal means there's two, well, it's normal to two things. It's normal to both the t and the n. Hey, quick question's going to ruin the surprise for you. How do you take two vectors and get one that is mutually orthogonal? What do you do? We're going to be using that. The binormal is going this way. So we have the t, we get the n, and we get that b going inward. And that gives us the direction of the twist of the airplane. It's not really easy for me to draw that binormal. Did you guys get the connotation of what that looks like? Now, true or false? Is that going to, look, is that, no true or false then. Is that going to change the next moment of time?
Yes.
Yeah, that's going to change every single moment. It's given us a unique frame of reference that's changing at every single point. That's what the TNB describes. That's what the Frenet-Serret frame describes. The same thing. Show of hands if you understand the concept of this thing. Okay. So we're going to do some examples. That's what the next section is for, on how to find these. There's a lot of work involved. This is not something you find really easily. I'll show you how to do it. And I do want to just kind of play on this a little bit. Because I took some time to make my paper airplane, man. I want to play on it a little bit. The direction the particle is heading, the nose of the plane. Think nose of the plane. So for our airplane, where the nose is pointing. So here you go. That's the T. That's the T. The N is where this tail fin is pointing. Do you guys see the interplay there? T is this way, N is this way. The tail fin is perpendicular to the T. It's perpendicular to where the nose is pointing. So the N is where the tail fin points. What's going to give us the B? Here's the nose, here's the tail fin. What gives us the B? the wings. The wings are both perpendicular to the T and they go this. Here's the T, here's the wings going this way, direction of the wings. Here's the T, well, here's the N, here's the wings. So it's perpendicular to both the T and the T and the N. The wings represent what the binomial does. Where the wings are pointing. Just please keep in mind what they are. Please keep in mind the idea behind it. Don't just do the math for the sake of math. Tell me something about these three vectors. What are they in relation to each other? Say that again.
Mutually orthogonal.
They're mutually orthogonal. They are just like IJK. They're just moving through space. That's what they represent. Also, they're just like IJK. What's the length of every single one of these vectors? Does that ever change for T, N, and B? No, so they have, those vectors have a constant length. They have a length of 1. We're going to use that in a minute. So these are unit vectors which are mutually orthogonal. Just like IJK, but moving with the particle. Now, that was what, 10 minutes, 15 minutes of just talking about the stuff. Did I make this stuff understandable for you? Do you understand the idea of this TNB, or the Frenet-Serret? We're going to say TNB because it's easier to say for us. Do you understand the idea of TNB frames? If you do, okay, what's T stand for? Everybody, what's T stand for? No, it doesn't stand for the tangent. It stands for the unit tangent. What's N stand for? Good. What's B stand for? The unit binormal. According to a plane, what's the T? Where it's pointing. What's the N? Tail fin, where it's turning, and the B is the binormal, how it's twisting. That's what that helps describe. So let's go ahead. Let's find out how to do it. And the next section gives us some examples on illustrating this concept. Are there any questions? I'm going to erase the board to go through a couple proofs here. Yes, no, maybe. Is it clear for you? You having fun? Is it interesting a little bit?
Yeah.
I think it's pretty cool. I get to make a paper airplane. Too bad I didn't bring my Imperial little, because that's perfect, right? It's got that big old fin and the wings, except you can't bring them down. You got to have them up. But that's pretty neat. So go buy one of those, and you got a perfect TNB frame. And then go buy me a lightsaber, because I've always wanted one, like forever. I've never got one. Which sucks. A grown man. Every grown man needs a lightsaber. Hello. Don't you know this? So how to find the TNB frame? How to TNB. The T stands for that unit tangent. We're going to use something that we talked about just a little while ago. Leave a little space here. Let's talk about that. Quickly, what in the world am I writing down right now? What is this?
Vector function.
Good, it's a vector function. It's parameterized in terms of what, everybody?
S.
Yeah, I know it's S. There's an S on the board. What's the S mean? What if I took a derivative? Come on, think through it. Don't just do the math, think through it. What's the derivative of a vector function give you? No.
Or tangent.
What's a derivative of just a unit vector in general? What's it give you? I'm losing you, huh? Let's think back a little bit. Do you know what derivatives do? They give you a slope of a line of point, but in 3D they give you a direction of a line of point that is tangent to every point at the curve. Make sense? What's the derivative of just a tangent? What's the derivative of a vector function give you? Very good. What's the derivative of a vector function give you if it's defined in terms of its arc length? The unit tangent. If you have done all the work that we've done already, if you have defined your vector function in terms of its arc length, you take a derivative, you're done. You just found the unit tangent. Now, obviously, we've done unit tangent before without arc length. So there's another way to do it. What if you didn't want to spend the time, because it's extensive, what if you didn't want to spend the time redefining this or reparameterizing this in terms of arc length? Could you still find the unit tangent without doing that?
Yes.
Okay, let's think it through. This is, everybody, what is it?
Vector function.
Good. How do you find the tangent vector to any vector function? Is this necessarily a unit tangent? How do I find a unit? Okay, how do I find a unit vector for any type of vector? What do I do?
Divide by the magnitude.
So if I find a vector function, take a derivative, divide by the magnitude of that vector function, this is also the unit tangent. Let's verify that. Here's a vector divided by the magnitude of the vector. That's a unit vector. This is a tangent vector divided by the magnitude of the tangent vector. It's a unit tangent vector. That's what the T stands for. This is typically how we do it. You know why? You know why? Number one, because these pieces are used in something we cover later called curvature. We haven't talked about that, but we're going to. Also, think about this. If you were to reparameterize by arc length, you've got to find that anyway, because you're integrating that to find the arc length. Do you guys see it? Now, it makes the next couple steps easier if you do it, but you're not winning either way. It's a lose-lose scenario. It's just a lot of work either way. So this is what the unit tangent means. This is why we learned how to reparameterize by arc length, but this is typically what we do. That's the all about it. Nothing fancy, just the derivative of the vector function divided by the magnitude, giving us a unit tangent. Now, how about the normal? Maybe you can do it. What do you think the unit normal would be? How would we get from here to the unit normal? What do you think? If I want something that is perpendicular to the tangent. So here's my nose. I want to find this is what t is. This is the vector of t. I want to find the vector for n. I want to find something that's tangent to the tangent and something that's perpendicular. How we do it, because it's not super obvious, how we find the unit normal. We take, provided you found this, the derivative of the unit tangent over the magnitude of the derivative of the unit tangent. Hey, if you've done this, second derivative. That's what makes it easier. If you haven't, which we're not going to do a lot of that, then we have to find the derivative of this thing divided by the magnitude of that thing. That's going to give us the unit normal. So, derivative of the vector function over magnitude, that gives us unit tangent. Derivative of unit tangent over magnitude, that gives us unit normal. Head nod if you're okay with at least the formulas. Now, this is not obvious. Is it true that this is perpendicular to this. We're gonna prove that right now because it's not an obvious thing. So let's firstly a little description. Unit normal. This is a unit vector that is perpendicular to t. How do we know? How do we know it's perpendicular? Here's a little statement. I'm going to prove this little statement here, then we're going to apply it to this scenario. Here's the statement. Every vector with a constant length is perpendicular to its tangent vector. Do you guys want to see the proof? I mean, would that be useful for you? Because it's not really obvious, to me at least, that this is perpendicular to that. If I find, look, we're kind of, I can see you're writing a lot, but you're not, some of you aren't focused on this, okay? Do you understand that when I take a derivative of something, I am for sure getting a tangent? When I take a derivative of this thing, I'm getting another tangent. Does that make sense? How do I know that this tangent is perpendicular to this vector? That is what we're about to prove right now. And it's with this statement, every vector with a constant length is perpendicular to its tangent vector. That's not a proof, that's just a statement. By the way, the reason why it's going to work for us, check this out. Verify this for me. This thing is going to have a constant length. What's its magnitude? Hey, that's a constant. It's not going to change. So the reason why this proof is going to work for us is because this is a unit vector, and therefore its length is 1. It is constant. Let me start the proof over here so I can do it one-sided. So let's let just a vector v, let's let v be a vector with constant length. Now, by definition, we know that if we dot product a vector with itself. Think about this for a second. I know there's a little formula because I told you a property of a long time ago, but think about it. If you have the same components, you have component squared plus component squared plus component squared, and if we have that, then basically we have the inside of the magnitude, right? Or we have the magnitude squared. There was a little definition I gave you as a property a long time ago when we first talked about dot products, but that was it. Do you remember that? Just a little bit? Well, we'll check it out. What's this stand for?
Magnitude.
If the magnitude is constant, then this would equal a constant. You just put constant. It's going to equal because constant squared, it's going to be a constant. If you're really just pedantic, you go, oh, well, the magnitude is a constant, so then this would equal, then this would equal a constant squared. Well, yeah, okay, but the constant squared is still going to be a constant. Does that make sense to you? Do you guys understand the idea? Hey, here, dot product equals magnitude squared. That's for any vector ever. Even vector functions, that's what we're talking about here, okay? So even vector functions, this works. But if the vector function has a constant magnitude, then I'm calling magnitude equals constant, magnitude squared would be constant squared. Since its magnitude would be a constant. You guys all right with it so far? Well, if these are vector if this is a vector function, if we take a derivative of both sides, tell me something. C squared, constant, true, false? Derivative of constant, everybody in class, what is that? For sure. This one, first time we've come across it, I haven't stated it in class because they're very easy. We have not talked about product rules for dot products, cross products, or vector functions. They are the same. Derivative of the first times the second plus the first times derivative of the second, even across the dot product. So this product rule would be derivative of the first dotted with the second plus the first dotted with the derivative of the second. They're the same product rules. They don't change, even across cross products. It'd be derivative first cross second plus first cross derivative second. Same product rules, don't mess them up, they're just product rule. Head nod if you're okay with that one so far. Now, how about this one? Are dot products commutative, yes or no?
Yes.
Since multiplication is commutative and addition is commutative, dot product is commutative, which means that this is the same thing as having two of this. This is this, that means, hey, this plus this is 2 of whichever one you want. It doesn't really matter. Let's divide both sides by 2. Can I do that effectively?
Yes.
You know what, I'm going to pick this one. It doesn't really matter, but... So if I divide by 2, well, here's what we have. Check it out. This is the proof. I've got a vector dotted with its, if this is a vector function, everyone in class right now, what's a derivative of a vector function? What is that? It's a tangent vector. I've got a vector function dotted with its tangent vector function, a vector with its tangent, and the dot product equals 0. What happens every time a dot product of two vectors equals 0? You had it on your first test. What does it mean? It means they're perpendicular. So it means that this vector is perpendicular to this vector. And what that proves for you, did you follow it? What that proves for you is that a vector and its tangent vector are perpendicular if the magnitude of that vector is constant. So for vectors that have constant length, the vector is perpendicular with its tangent vector. Does that help us here? Well, let's see. Is t a vector such that it has a constant length?
Yes.
Well then, t's got to be perpendicular to the derivative of t. If you didn't follow it the first time, like 10-second recap, here's what we're doing. Take a vector that's got a constant length. Cool, dot product. It's got to be equal to this by any vector like ever, okay? But if the magnitude is constant, so even with vector functions, if the magnitude is constant, call it a constant. Take a derivative of both sides. Product rule still works, cool. Derivative of constants are 0. Oh, but wait. Commutativity. If a dot product equals 0, the vectors here are perpendicular. Since t is a unit vector, it has a length that's constant. It has a length of 1. That doesn't change for unit tangents. Therefore, this would also work with t. That means that t dotted with the derivative of t is 0. That means that t is perpendicular to the derivative of t. It means the tangent vector is perpendicular to the, that's hard to say, but the tangent to the unit tangent is perpendicular to the tangent vector, the unit tangent vector. So this vector perpendicular to its tangent. Okay, but wait, there's just a little more. Is it true? If this is true, which it is because I just proved it, it's a vector with constant length, it fits this paradigm, we're done. Is this also true? Let's see.
Yes.
You believe this one?
Yes.
So here's the question. This is not necessarily a unit vector. This one is a unit vector. Did you guys see it right there? Here's the vector, here's the magnitude of the vector, that's a unit vector. Is this in the same direction as this? That's a definition of unit vectors. That's the definition. It's literally the direction. So if this is the direction of this vector, just as a unit length, then it's got to also be perpendicular. But wait, this is n, and that proves it. That proves right there that t and n are actually perpendicular by doing that little proof. So, same direction, just unit vector, and then that's what n is. That is what the unit normal actually is. Show of hands if you understand the proof. It's pretty cool. If you didn't, you can still do the stuff, but I'd like you to understand it. Now, how about this one? The b is the unit binormal. There's no fancy, it's kind of a simple proof, but there's no proofs for this one. Here's why. If you have a vector t and you have a vector n, which we just proved they are perpendicular, but even if they weren't, I don't even care. How do you find a vector that is perpendicular orthogonal to both of them? Here's t, here's n, I want this one. How do you do it? Cross product. So b, very easy. B, therefore, has to be equal to t cross n. That's the definition of what a cross product gives you. So t is orthogonal to n. If I cross product t and n, we get b, which is orthogonal to both of them. We have this mutually orthogonal system that moves through space. That's the nature of the cross product. Did this make sense, actually, to what we're talking about?
Yes.
Okay. Any questions?
I was just wondering, this is kind of a theoretical question. Would you be able to solve for, like, b cross t should equal n also, right?
It does. Yeah, it absolutely does.
So you could solve.
Just like you can cross I and j and get k. You can cross j and k and get I. You can cross I and k and get, I said that one already. I and j and cross any two, right? You did the other one. Same thing happens here. The same exact thing happens. Okay, I'm going to stop it here.